Hello and welcome once again for another ES340 video. This is day 10, part A. I believe there will probably only be one part to this video, to this lecture. Okay, so now we're moving on to, we've discussed the first law of thermodynamics, which studied the energy balance equation and the energy balance rate equation, right? So we were really looking at the conservation of energy in the for the first law of thermodynamics. The second law of thermodynamics helps us to explain things that the first law just cannot explain. An example would be a hot cup of coffee, right? So imagine I have a nice hot cup of coffee, or tea, or whatever it is that you like to drink, and you know full well that heat leaves the cup of coffee, and eventually, if you let it sit out long enough, the temperature reaches an equilibrium with room temperature. So it cools off until it reaches room temperature. You can also have, melting blocks of ice, right? If I have a block of ice sitting on a counter or something like this, eventually it melts into, a puddle of water. And eventually that puddle of water will also equilibrate to the temperature of the room. Okay, so we have these processes, and we call these spontaneous processes. And what do we mean by that is if we leave the cup of coffee to its own device, it will always cool off until it reaches room temperature. If we leave the block of ice for long enough, it will always heat up until it reaches room temperature. And so the reason for this is that these are spontaneous processes. You never see it go in the other direction. You never see the cup of coffee getting warmer by drawing heat from the room. However, there is nothing that actually prevents this from happening according to the first law of thermodynamics. And we'll discuss this in a moment. The second law of thermodynamics just kind of takes note of the fact that we have these spontaneous processes, and this is not something that's explained by the first law of thermodynamics. So because of this, then these spontaneous processes are going to be a key part of the second law of thermodynamics. So we'll notice the cup of coffee example, of course, is a good one, and easy to see in thermodynamics. But there are other things, even in mechanics and things, that we can see this. For instance, if I were to take a mass and hang it off of a pulley that's attached to the ceiling, and I let go of the mass, it's going to fall until it hits the floor. Spontaneously, that's the direction of motion. It doesn't mean that it couldn't go in the other direction. In fact, it's entirely possible. It could draw energy from the room, from the air in the room, and be pulled up, but that's not what we see. We see spontaneously the mass falling to the floor. Okay, so these spontaneous processes are really important, things that happen spontaneously, whereas the reverse direction does not happen in general without some kind of input, work being done or something like that. So we can actually take advantage of the fact that we have these spontaneous processes because they allow us to actually perform work while they're not in equilibrium. Of course, this implies that there is a practical limit to the amount of work that can be extracted from such a system. We're going to talk about this part a little bit, or much more detail later, but there's also this concept of something called entropy. And I really want to discuss entropy in more detail in a future lecture. So I'm going to reserve a future lecture for this. However, I'm going to note that the second law of thermodynamics can really be written as this one simple equation. The change in entropy, which is given by S, capital S for entropy and lowercase s for specific entropy. The change in entropy of an isolated system is always greater than or equal to 0. And this is really, it's kind of hard. This is why I'm going to reserve time in a future lecture to discuss this. But you can sort of think of this in terms of how well organized a system is. That's one way of thinking about it. So if there's a lot of disorder, then we would say that system has a large amount of entropy. So basically, what it's saying is that isolated systems always move towards more and more disorder until it reaches some maximum value. There is a limit. It doesn't go off to infinity, but until it reaches some, basically once equilibrium is reached, it will tend to go to maximum disorder. And the way that you can actually bring things back out of the disorder is by applying energy. So you can you can apply energy to make things more orderly, but the cost is that the entropy is always increasing in an isolated system. Now, if we take the universe itself to be an isolated system, that means that the entropy of the universe is always increasing. But locally, we can have things that violate this because they're not isolated, actually. In reality, Earth itself, for instance, is not an isolated system. In fact, it has an input of energy from the sun. But we'll discuss this in more detail briefly. So let's do the first clicker question. A process in which the change in entropy is 0 for an isolated system is best described as a... Oh, I didn't discuss reversibility yet. Hold on. So let's discuss reversibility before a brief discussion of reversibility before asking this clicker question. When something is reversible, that means that it can be taken back to its original state. The whole system, the system plus its environment can go back to the initial state. This is a very strict kind of thing that can happen. So a system is irreversible if you cannot return that system back to its initial state without some kind of other input from the environment. If you have an input from the environment, that means that the environment itself cannot be returned to its initial configuration, its initial state. So that would be irreversible. Okay, and we'll discuss that. Actually, I'll probably reserve this problem because until the end of the video, because we're going to discuss reversibility and irreversibility in even more detail in a moment. So maybe we'll take this clicker question and push it off to the next until after the end of the video. So the second law of thermodynamics, we've already kind of seen, we discussed the spontaneity, right? Things, for instance, you might expect that if I took a gas and I put it into a vacuum in space, that it would just expand, it would expand forever, spontaneously. You would not expect to see it kind of compress itself. You would expect to see it go on an expansion. That's an example of spontaneity. The temperature, the change in temperature to the trying to equilibrate to the environmental temperature, that's a spontaneous transition. You don't expect to see it go in the opposite direction where things get either much hotter or much colder than the environment, right? Without some kind of external input, like a refrigerator needs actually to take in energy in order to make the contents continuously stay cooler than the environment. So without an input, without that additional input in energy from the environment, we cannot make a refrigerator operate, right? So the second law of thermodynamics is really related to these things. And there's a couple of different statements of the second law, and we'll explore the meaning of these. But basically, the reason for the second law arose was to explain situations that couldn't be explained just by the first law. The example of the temperature, there's nothing in the first law that bars something from drawing extra energy from the atmosphere in order to get warmer. There's nothing in the first law that bars that situation from happening. You can still balance the energy equation by doing that. But there's something more fundamental and deep going on that requires this explanation using the second law of thermodynamics. So that's the reason why we discuss this. And let's start with the Clausius statement. It is impossible for any system to operate in such a way that the sole result would be an energy transfer from a cooler to a hotter body. So the basic idea there is that you couldn't take, say, the block of ice, and this is a Clausius statement. You couldn't take a block of ice and transfer heat from the ice to the environment spontaneously. Right? We know that spontaneously it goes in the other direction, in fact, that the ice tends to absorb heat from the environment and melt. So you wouldn't expect the ice to kind of warm up the room, and while at the same time making itself cooler, right, by radiating off some heat or something or something like that by convection or whatnot. You wouldn't expect such a case to happen. So the sole result cannot be transfer of heat from a cooler body to a warmer one. That's the Clausius statement of the second law. Now, again, refrigerators do this, but they do so by having an input of energy. So they cannot have, so the sole result is not just that heat is going from cold to hot, but rather there's also an input of work from the refrigerator that's allowing us to do so. So there's something else that's going on in that system allowing us to cool off the refrigerator, right? So there is more than just heat flowing from cold to hot, there's also work that's coming into the system, which is what allows us to do this. A refrigerator does not actually violate Clausius' statement of the second law because of the fact that we're adding in work as well. So you can't just have heat flowing from cold to hot. You can have work happening, which is drawing heat from cold to hot, but you can't just have heat going from cold to hot. The next statement is the Clausius statement, the Kelvin-Planck statement, of the second law of thermodynamics. It is impossible for any system to operate in a thermodynamic cycle, and we're going to be discussing cycles a lot, so I do want to get familiar with this, want you to get familiar with this, and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. And this word single, I really cannot highlight it enough. I want to highlight it multiple times. It is possible if we have multiple reservoirs, thermal reservoirs, but it is not possible with a single thermal reservoir. So the example goes something like this. We have a thermal reservoir. We have some heat going into the cycle from the thermal reservoir. And we have, so this is our system. We have the little cycle. We have a cycle happening somewhere in the system. Let me put the cycle like this. And we have some work being done by the cycle. This is impossible. So if I do not have multiple reservoirs, if I had only a single reservoir, and it's kind of hard to imagine even a scenario with a single reservoir where it's just, just hot and nothing else, or just cold and nothing else. But if I am operating in such a system where that is the case, where I have a single thermal reservoir, maybe maybe thinking about the ocean or something like that as the thermal reservoir, and I'm drawing heat from the thermal reservoir, and I want to make a thermodynamic cycle that extracts work from that case. This is impossible. It cannot be done. Now it can be with two, but not with one. Okay, and so the reason that we want to do this is that we want to be able to analyze systems, and sometimes we can actually break systems into pieces where you do have something like a single thermal, that you can break it into a couple of pieces where there's a single thermal reservoir connected to a cycle or something like that, and we can analyze the system in that way. Now, what does this imply? We call this the analytical form of the Kelvin-Planck statement. It implies that the work of the cycle has to be less than or equal to zero. If it's equal to, as we'll see soon, if it's equal to zero, that implies that there are no internal irreversibilities, and we haven't talked about internal irreversibilities yet, but we will in a moment. So if there are no internal irreversibilities, then the work done by the cycle is just going to be zero in this case, if I'm attached to a single reservoir. Otherwise, the work has to be negative. In other words, you have to have an input of work from the cycle, from the environment. I mean, you have to have an input of work from the environment into the cycle in order for this to work. So you can't just draw heat out of, say, a cold reservoir, as an example, just by and then also expect to use that heat to do work from the cycle. So you would have to input work in that scenario in order to make this system work. This whole thing is impossible. And then there's a third statement of the second law of thermodynamics, which says that it is impossible for any system to operate in such a way that entropy is destroyed. So entropy is not, I should note this, entropy is not conserved. It can be created, but not destroyed. And we kind of saw that statement up here, that the entropy of an isolated system has to be greater than, the change in entropy has to be greater than or equal to 0. So we have, if we account for both the system and its environment, zooming out to the whole universe, we always have to see entropy increasing, which means that we're creating entropy in an isolated system. Okay, so now as I said, I wanted to discuss irreversible and reversible processes in a little bit more detail. So an irreversible process is one that cannot be restored to its original state along with its environment. So what I mean by that is you can't restore both the environment and the system back to its original state. It's impossible to do so if we're talking about an irreversible system. A reversible system is obviously one that can be restored along with its environment to its initial state. So it turns out that actually, in order for a process to be reversible, the process must be quasi-static. So there's a reason for this. It cannot have finite temperature differences. We can't have finite temperature differences in a reversible process, and we'll discuss that in a moment. So in order to be reversible, it must be quasi-static, which means that we must be making very slow changes and moving through a series of equilibrium states, right? So we have to move very slowly through a series of equilibrium states in order to be reversible. And that's the only way that you can have temperature differences that are not finite, being so small that we wouldn't consider them finite temperature differences. Now, the reason for this is because the moment that you create some kind of spontaneity, right? This was really what these two statements, although it might be hard to see at the moment, but I want you to think through why that is. Both of these statements really are saying something about spontaneity here. And the first one is probably easier to see, the Clausius statement, than the second one. It's a little harder to see why this is true in because of spontaneous processes. But basically, if you have a finite temperature difference, then there is going to be spontaneous heat transfer that happens. Once you have a finite temperature difference, spontaneous heat flow will happen, and you end up with problems because of these different statements of the second law. So you cannot go backwards and restore the original state for both the system and the environment in such a case. Okay, so let me just discuss irreversible processes a little more. Let's do some examples. One is, of course, I just mentioned heat transfer through finite temperature differences. Once that happens, you kind of make the environment more disorderly, which means it cannot be restored back. So this is related to spontaneity. Another one that is important is friction. So when you have friction, basically, you're obviously removing energy from the system, and there is actually typically heat transfer that's associated with friction. So you're removing energy from the original system, and it can't just spontaneously be restored back to its original state. You can also think of things like a rubber band being stretched too far. This has to do with deformation, inelastically. So we know that rubber bands are elastic, but there is some, if you stretch it too far, it kind of just gets stretched and doesn't return back to its initial state. You can try this, it's very easy. You'll see that it stretches further. If you stretch it too far, it doesn't come back to its natural resting length that it was at before. And that's actually called something special called hysteresis. But basically, because it can't be restored back to its initial state, this is probably the easiest one to actually see when the system cannot be restored back to its initial state. It is irreversible. Okay, so these are examples of irreversibilities, and there's more. Your textbook does a good job explaining a bunch of these different types of things. So one for reversible processes, this is kind of harder to come up with, but a frictionless pendulum is an example. So the idea here is that you can even see when it gets restored back to its initial state. In this case, you don't always have to necessarily see the process itself doesn't have to necessarily restore it. It's just that it could be restored is the whole point. But in this case, the pendulum case, it's kind of easy to see when it gets restored back to its initial state because it continuously swings back and forth, right? It's going to come back and forth, and since it's frictionless, it's not going to be constantly losing energy to friction via heat going to the environment or something like that. So it's not affecting the environment at all if it's frictionless, and it's swinging back and forth. So it after a certain period of time, it is restored back to its initial state, whatever state you choose as the initial state. Maybe it's this state straight up and down. As it swings, eventually at some point it comes back through that point of being straight up and down, and then it passes on through and comes back. So periodically it actually revisits that initial state, and so in that case it is in fact reversible. Another one is your book likes to use is the gas, and we have a piston cylinder type assembly. And in that case, if it is with no heat transfer, so we can actually imagine a case where we very slowly, say, compress the piston. It's going to pass through a series of equilibrium states, and if there's no heat transfer, then you can imagine that at each point there is no real temperature difference that we're passing through. So because of that, there's no spontaneous heat transfer happening in this quasi-static process. So it is actually a requirement that the process be quasi-static. But just because a process is quasi-static does not mean it's reversible, though. So you have to keep those in mind. So to be reversible, I'm going to write this, must be quasi-static. But quasi-static does not mean reversible. They can't be interchanged. These terms are not interchangeable. Some quasi-static processes are in fact not reversible because they might have friction or other things that we mentioned above here that make them irreversible. So be careful with this, and I think you're going to need some time to digest what all of this stuff means. So we will be doing some examples to try to really. I think it's very hard without examples to flesh out what is meant by all of this. So keep in mind we'll be doing some examples to kind of figure out what's going on here. Now, the final thing that I wanted to discuss today was the Kelvin-Planck statement, the analytical form of the Kelvin-Planck statement. So what is the Kelvin? This is going to actually be really important for us. The Kelvin-Planck statement implies, remember up here we even wrote this, that the work of the cycle must be less than or equal to 0 in a single reservoir. I need to come back down here and write single reservoir. Again, if I have multiple reservoirs, this does not apply. So I want to make that very clear. If there's multiple reservoirs, this does not apply, but for a single reservoir, it does. What this means then is if the work of the cycle is equal to 0, process is internally reversible. And I'm going to discuss internally reversible in a minute. Work of cycle less than 0, again, single reservoir, then the process is irreversible. Okay, so what does internally reversible mean? If the system is reversible, but the environment, the effect on the environment are not reversible, then we say internally reversible. Okay, so you can imagine things like an example is, let's say you pass water through a condenser. So when the water passes through the condenser, it say maybe it starts off as steam, and then it turns into liquid water. So you have some condensation that's happening. In that case, you can obviously return the water back to its original state. You could pass it now back through heat it back up, return it back to steam. You can pass it directly back to its original state, including all of the properties that it had before, the same pressure, the same temperature, and whatnot. But during the process, when you were passing it through the condenser, it was giving off heat to the environment, right? So the environment itself felt heat transfer, and it was not at a finite, it was at a finite temperature difference that this was happening, because the environment obviously was at a different temperature in order for you to get this condensation than the system itself, the water itself. So when you did that, the water itself can very easily be moved back to its original state, but the environment cannot, because there was this heat transfer that happened at a finite temperature difference. Okay, so that's one of our primary irreversibilities. So the environment now, it had some irreversibilities that happened to it, but the system itself did not. So this is an internally reversible process. Okay, and we're going to do some more examples in the example problems. That's all that I have for this video. Hope to see you again soon.